All right, ready to start our next unit, unit number 4, trig functions. And the focus of this lesson is going to be on radian measure. So we're going to start working with different modes on your calculator other than just degrees. Our learning goals, we're going to use radians to represent angles and then solve some problems. So what is radian measure? Well, the first thing you should do is draw that diagram, a circle, and you have a radius, and then you have 1 radian. And 1 radian is when you have a radius, and then you have the arc length that is equal to the radius. And the arc length is just the distance around a curve. So when you take that distance, when the arc length equals the radian, that is, or sorry, when the arc length equals the radius, that represents 1 radian. All it is essentially is another unit of measure. Angles are commonly measured in degrees, but also in radians. And radians are a pure number. 1 radian equals the size of the central angle when the arc length is equal to the radius. So 1 radian is slightly less, and we're going to actually figure out the conversion of this, but 1 radian is slightly less than 60 degrees. And radians are often confusing. It's kind of the equivalent of like degrees to radians is kind of like inches to centimeters, kind of like two different units of measure to measure the same thing. Now, that's distance. We're talking about degrees or an angle inside. We're talking about angles inside of a circle or inside of a triangle for that matter. So 1 radian is our central angle. So we're going to add some things to this picture. So from here to here, that would be like theta, and that would be 1 radian. And you could split that up into, approximately, if it's 60 degrees, if we do some quick math, just over 6 radians-ish. So you could split that circle up into, 6.28 radians, let's say. And we'll come back. That number may stick out to some of you. But to help, show you the difference between degrees and radians, what a radian is, I could take this circle and I could split it up into, now this isn't to scale, obviously, but I could split this up into 360 of those little pie slices. And that would all be 1 degree, 1 degree, 1 degree, 1 degree. And if I go all the way around, there would be 360 of them. So a radian is just a different measure, a larger measure. Obviously, you can see 1 radian is quite a bit larger than 1 degree. And we have a formula, theta equals A over R. It's a simple formula. A stands for the arc length. R stands for the radius. And theta equals the central angle. But to be able to use this formula, your central angle always has to be in radians. If it's in degrees, you have to convert it to radians, which we will get to later in this lesson. So our first example, a circle has a radius of 4.5 centimeters and has an arc length of 10 centimeters. What is the central angle that subtends these measures? Subtends just means between. So first thing you should always take a look at, make sure that your units of measure are the same. This is centimeters, this is centimeters, that's good. If it was centimeters and meters, you'd have to do a quick conversion there. So we're going to use our formula. This is asking us for the central angle. We're using our formula we just saw, theta equals A over R. It's a pretty simple formula. My arc length is 10 centimeters. My radius is 4.5 centimeters. And if we use our calculator, 10 divided by 4.5, we get, now you get 2.22. I would really like us for 12U students to keep things in terms of fractions, unless it's a nice decimal, which 2.2222222 is not a nice decimal. So I'm going to write that as 20 over 9 and rad for radians. That would be an exact answer. If it asked you for an approximate answer, then you could round and it would be 2.2 radians. Again, rad just stands for radians. So if you had those measurements, 2.2222 rads, so those pie slices that we just saw in the previous slide, be 2 of those plus a little bit of our circle. So that brings us to being able to get to conversions. And here's a question that's going to help us. What is the central angle of an entire circle? So let's draw a picture first. So I'm going to draw a circle. And we'll put a point in the middle. And we'll go out to the edge. And we'll say that's the radius. So I want the central angle of the entire circle, not just 1 radian, 2 radians, or an angle that subtends an arc length and a radius. I want to go all the way around. That's my theta, and that's what I want to know. Well, there is a formula that we can use for arc length, even though it's not called arc length, but basically, I'll take a different color here. So we want to know what that angle is. Well, what's the arc length? I can go all the way around. That would be my arc length of my angle. Okay, so going all the way around. I found on the web. It's going all the way around. That's also known as the circumference. And you might remember that formula as 2 pi r. Even though we don't call it that when we see that in like grade 8, grade 9, grade 10, we that's your arc length, the circumference, the distance all the way around the circle. So we can use that actually with our formula that we just saw. So theta equals A over R. I know what my arc length is. It's my circumference of my circle, which is 2 pi r. So 2 pi r over r. And look at that. The r's cancel. Theta equals 2 pi. So 2 pi, which radians and pi kind of become synonymous, but they're not the same thing. And you're going to have to make that very clear as we move forward through this unit and the next unit. Pi is not the same thing as radians. Pi is 3.14 radians. It's 3.14 of something. It's just pi is a nice number, right? At least when it's written as a pi symbol. So that gives us our kind of conversion factor. So I know that in one circle there's 360 degrees. I also now know that in one circle there are 2 pi rad, 2 pi radians, which if you're wondering where I got 6.28 from before, 3.14 times 2 is 6.28. So we know that one full circle is 360 degrees. We also now know that it's 2 pi rad, radians. If I divide both those by 2, well, those 2's cancel, and I now get 180 degrees equals pi radians. I guess I can write that, pi rad. And that right there is our conversion factor. So 180 degrees equals pi. 3.14 radians equals 180 degrees. Our next example, we're going to convert each measure to radians. It is pretty simple to do this. I'm going to show you kind of a long way to do this using ratios. It's a surefire way to get the correct answer because conversions sometimes mess with people's heads, but this certainly isn't the only way you could do this. But if I want to know how many radians there are, you could use your conversion factor. So pi over 180, and I'm starting with pi on top because I want radians. And x over 90, which is this. And one thing you're going to notice, this is pi rad, and I want to know x rad, how many radians is 90 degrees. And here we have degrees on the bottom and degrees on the bottom here. So all you have to do is cross multiply to get rid of that. So 90 pi over 180 equals x. And then you just have to simplify that. What does 90 over 180 simplify to? Well, that just simplifies to 1/2. So x equals pi over 2. You could write 1 pi over 2, but that doesn't. It's redundant to write that 1 out front. So x equals pi over 2. Just by looking at the last slide, pi is 180. Obviously, 90 degrees is half of that. This just algebraically proves that. 30 degrees. Let's start the same way. Pi rad over 180 degrees. That's our conversion factor. I want to know what x radians is 30 degrees. Cross multiply. 30 pi over 180 equals x. Reduce that fraction. 30 over 180 is just 1/6. X equals pi over 6. Negative 150, even though it's negative, same idea. Conversion factor, pi over 180. X over negative 150, cross multiply, negative 150 pi over 180 equals x. Reduce that fraction, negative 5/6 pi equals x. Or even cleaner, write it like that, negative 5 pi over 6, as opposed to negative 5/6 pi. Same thing. 510 degrees, again, same idea, pi over 180, x over 510, cross multiply, 510 pi over 180 equals x, reduce that fraction. So as you can see already, we are going to have to work with fractions a lot. And part of the next 2 units, this unit plus the next one, is going to rely on your ability to not only be comfortable with working with fractions, but reducing fractions, or at least knowing how to use your calculator to reduce fractions. Example number 3, we're going to work the other way, convert each measure to degrees. So we have pi over 2. Well, we already know that pi equals 180. That's just a straight substitution. So we could set up a ratio if we wanted to in this case, but this is just an easy straight substitution, right? You know pi is 180, so you right off the bat sub in 180 for pi. And that equals 90 degrees. So make a little note there. That's just a straight substitution. Same thing here. Negative 4 pi over 3, that's just a straight substitution. Sub in 180 for pi. -4 times 180 divided by 3, type that in your calculator. Hopefully you get -240 degrees. Now here's where things get a little bit different. Instead of giving it to you in terms of pi, I've now given it to you as a pure number as radians, so 1 radian. Well, we're still going to use our conversion factor, and we can set up a ratio here. But instead of it being pi over 180, I want to go the other way. I want it to be 180 over pi. You'll see why in a second. And again, that's pi rad. So what happens here is these radians cancel. Rads cancel with rads, and you're left with 180 over pi. So instead of it being pi over 180, it's 180 over pi. And if you type that into your calculator, you're going to get 1 radian equals, now if we round to 1 decimal place, 57.3 degrees. So 1 radian equals 57.3 degrees. This is another conversion factor you could use. It's not useful to use that when you have your angles measured in terms of pi, but when I give it to you, instead of giving it to you in terms of pi, I give it to you as a decimal or a whole number, this is the better conversion factor to use. So when we go to D, 1.75 radians, that's just simply, I know 1 rad equals 57.3 degrees. That's just a straight substitution, right? 1.75 times 57.3, and if we go to 1 decimal place, 100.3 degrees. So like I said at the beginning, 1 radian is slightly less than 60. So that's why half a circle is 3.14, 180 degrees, and a full circle slightly over 6 radians, 6.28. So now that we know how to convert, we're going to go on to our next example. A circle has a radius of 80 meters. Determine the arc length of a central angle of 40 degrees. Your first step from going back to the beginning, your central angle is always measured in radians. So you have to convert degrees to radians first. Well, we just learned how to do that. Set up a ratio, x over 40 equals pi over 180. Cross multiply. X equals 40 pi over 180. Reduce that fraction, you get 2 pi over 9. So now we know that theta is 2 pi over 9. So that's x, it's asking for our central angle, theta. Using our formula, theta equals a over r. 2 pi over 9 equals, I'm looking for the arc length. The radius is 80 meters. I'll include the units here. Cross multiply, so it would be 2 pi times 80 meters over 9 equals the arc length. And then 2 pi times 80. Whenever you're using pi to multiply, just leave pi alone. So don't type in 2 times pi times 80 because your calculator is going to give you a decimal. Type in just the whole numbers and leave pi. We want to leave things in terms of pi because it's a much nicer number to look at. So 2 times 80 is 160. 160 pi over 9 meters equals A. That is your exact solution. Or if it asked you for the approximate solution, it would be 55.9 meters. Example number 6. So if you've taken physics already, you may have seen something like this, angular velocity. And this is a question or something like this that you may see pop up in an important place or two coming up. So angular velocity refers to how many radians, or it could be degrees, something is moving in a circular motion over time. Usually it's measured in rads per second, but it could be measured in degrees per second as well. Or we don't do it in high school, but there's like another way you can measure angles and it's gradients, but don't even worry about that. We're not going to do gradients. So usually radians per second is what I would prefer. So our example, a bike wheel with radius 20 centimeters rotates 10 times in 30 seconds. Determine the angular velocity in rads per second and determine how far the bike has traveled in 3 minutes. So this is a two-part question. To set this up, okay, velocity. Now you don't have to write it like this, but velocity is a vector quantity and velocity is distance over time, displacement over time, I guess I should say, but distance over time, kind of setting it up. But it's not asking you necessarily, it's asking you for radians. So the distance isn't like how many centimeters it's traveling per second. It's like how many, not degrees, but how many radians. So how much of an angle is it turning through? So in this case, distance is not measured in terms of centimeters. It's going to be measured in terms of radians, which is how fast it's turning. And that gives us our rads per second. Okay. So to come up with our distance, we know, okay, that how many radians are there in a full circle or in a full revolution? Well, we know that there are 2 pi, right? We just came up with that. So every time the bike wheel turns once, it's traveled 2 pi radians. But this tells you, we want it in rads per second, this tells you that it rotates 10 times in 30 seconds. So we actually have to do this times 10 over 30. And that would be 30 seconds. So again, just to re-go over this, distance, or the amount of angle that the wheel is turning through. Every time the wheel turns 1 full revolution, it's 2 pi radians. But it does that 10 times every 30 seconds. So this is going to give us our radians per second. So if we were to do 2 times 10, that's 20. 20 over 30 reduces to 2 pi over 3 rads per second. So this bike wheel is rotating 2 pi over 3 radians per second. If it asked you for an approximate answer, you could round that, and it would round to, I believe, 2.09 rads per second. So this wheel is rotating at 2.09, so just over 2 rads per second. If degrees makes more sense to you, remember we had 1 rad equals 57.3 degrees, so this is basically rotating through at 114.6, just over that, 114.6 degrees every second. So there is our angular velocity. So that takes care of this. We want to know, though, how far the bike has traveled in 3 minutes. There's a couple of different ways to do this. One of the ways to do this actually doesn't even involve using our angular velocity. You could actually use your angular velocity if you wanted to, but let's come up with a different way just to show you something different. So we know that distance, so distance around a wheel, that's circumference. And as the wheel touches the ground, it's moving forward, right? And it's moving, if you were to cut the outside of the tire and lay it flat, that length is how far each revolution of your tire travels as you're moving forward. So the key word there is the circumference of your wheel times how many revolutions you do. Circumference is easy. It's 2 pi r, which is 2 pi times the radius, which was 20 centimeters. Now the number of revolutions, how many times does this go around in 3 minutes? Well, if it goes around 10 times in 30 seconds, how many seconds are in a minute? 60. So if it goes 10 times in 30 seconds, how many times does it go in a minute? Well, it goes 20. 20 times per minute, and it says in 3 minutes. What's 20 times 3? 60. So this does 60 revolutions. And if we do that math without entering pi, we would get 2 times 20 is 40 times 60 is 2400. 2400 pi centimeters is how far it would travel. If you were asked an approximate answer, you would do 2400 times pi. You would get 7,539.8. 7,539.8 centimeters. And again, that's the approximate solution. With rounding, this is the exact solution.